Thank you, Gary. Hi, everyone. Appreciate your attention. I decided to take a little bit more general, more broad approach than than maybe Gary was even requesting. Going last, I figured all the thunder had been taken by some of the earlier talks in the session. So hopefully if you're a customer out there, the other thing is I realize MSST isn't just about HPC and checkpoint restart. So if you're a customer out there, hopefully this will inspire you to be more specific about how you specify your requirements, maybe give you some insight from a vendor's point of view. And if you're a vendor out there, perhaps this will help you we'll commiserate together, and maybe stimulate some discussion, microphones afterward during the panel. So this is what I see as a typical I/O subsystem. And it's interesting, Dave's workflow diagram looked disturbingly similar to this as he started his talk. And ironically, I was thinking about using the elephant example as well, because that's some of the challenge that most customers have when they try to articulate to vendors such as ourselves exactly what's going on inside their systems. They focus on their applications, they focus on what outputs they want, but they really don't understand the intricacies and the complexities of the systems that they're working on. And I liken this to plumbing because it is very similar. I mean, because we're using a common set of parts. You know, we're using some fabrics. We're using certain types of solid state or spinning storage media. The component parts are very similar. PCIe fabrics, SSDs, and of course software, RAID strategies to do all this. But every single situation is going to be different. And you can bend these pipes in infinite ways. So every customer is going to have a unique set of requirements. Even within a specific vertical market, you know, I can look at a video surveillance application, or I can look at a medical imaging application. And even if they're using the same set of software, they're going to have a very different set of use cases to solve their problem uniquely. You look at any typical file system, and you see a whole lot of tuning knobs. You dig under the covers, and you find that there are various ways to shift the block sizes and shift the buffering characteristics, and even at the APIs, they have different functionality because the applications are so widely varied in their I/O requirements. Right? And as much as we try to make more sizes, make less software fit more sizes without those tuning parameters, invariably we find that we have to do that. So storage and I/O are often called out when there's a problem. If the customer, when I get an RFP and we look it over, and we see storage actually called out in an RFP, that generally means the customer's got a problem. They have had a chronic problem for quite some time. If we don't see I/O in the RFP, it's just assumed to work. It's funny how storage customers think about it in terms of capacity, but they don't really think about it in terms of the complexity, unless it's been a problem for them. So that's just a clue that we use when we're looking and responding to RFPs. And of course, the devil is in the details. Usually a customer will give you a very broad perspective on what the applications are supposed to be doing, but they really don't even understand in some cases what the I/O patterns are underneath the covers. And I'll give you a couple of examples of where there are some gotchas and potentially opportunities for improvement. I mean, Don knows this in spades. He's been at this much longer than me. Customers may think they know how the data flows through their systems, but if you ask some detailed questions about, you know, where does the data come from? What are your objectives? What do you really want to do with the data? You'll find out that they often don't really know. And this is what Gary and company are discovering as they go through the process of defining this taxonomy for workflows. We know a lot about our applications, but we don't know all the things that influence and impact the storage subsystem, especially when we start running multiple applications at once. And in the HPC space, that's what we're doing. We're building bigger and bigger machines, but what that means is that we tend to fractionalize those machines more frequently, and then we get multiple complex workloads interacting with one another. And the storage system needs to be reliable and predictable and not crater when we have increased complexity. So these monolithic workloads are actually the exception more than the rule, even on some of the HPC systems today. Some customers consider the workflow a differentiator. We've had difficulty actually getting information out of the customer. They want to buy a storage system, they want to buy a fabric, they need a certain capacity, and they give us some SLAs, but they also say, I don't really want to share with you all the details about how this works inside because I use this as a differentiator. A good example is in life sciences, genomics research, doing sequencing, processing a lot of data, and the faster I can get that done, the more money I make, and the more my genomics research organization is valued by the industry as compared to another. And so they don't want to share necessarily how their workflow might operate internally when it's essential to getting the bid put together. So these are some of the challenges we face when we're trying to analyze these workloads. Analytics users usually understand their workloads better than just about anybody else because their industry is about the data. I talked to a customer who has a real-time requirement. He's got data coming in from a lot of feeds for clickstream information. Customers clicking on web pages, and we need to serve as ads to them, for example. And we have another set of inputs that are the advertisers who have particular products that they want to put on the web pages. And I know we all hate all these bugs popping up everywhere, but this is a real industry today, and it's a growing one, and it's very profitable. Then we have, of course, what the market will bear. There are a variety of other factors, and in real time, the software has to decide what ad to put on what bug and what screen on what browser dynamically, situation moment by moment by moment. So there really isn't a large storage requirement here, but there's a large streaming workload, streaming pipeline of processing necessary. And so we arrange the pipes in different ways and put valves in different spots to actually achieve these kinds of interesting goals. So in my opinion, every situation is different and needs to be analyzed about all the ways the data flows and needs to be transformed throughout the process in order to build an I/O subsystem that's satisfactory for the particular use case. HPC users running similar workloads, well-tuned. I mentioned that's great, and a lot of them are older and are doing monster I/Os, but that may not be the most appropriate thing in the days of SSD. We tune these applications for running issuing monster I/Os to classic RAID subsystems so that we can avoid disk crashing. But that might not be the ideal workflow for later, or I/O profile for later storage technologies. So a couple of use cases I wanted to share, more examples that I've seen in the industry. An all-read query model. We have a customer who's collecting a bunch of data from sensors, just pouring in, constant data pouring in, and pre-processes that data to prepare it for query-based analysis, right? So it lands in a certain spot, we pre-process it, and then we load that periodically into a number of SSD-based servers. Right? So we have a large number of SSD-based servers that get loaded periodically, and then we do searches across those SSDs for a certain period of time until the data gets stale enough, and then we have to reload it. So here's one example of a workflow that differs dramatically from many others. Right? So you have to look, again, at the specifics. The GPU load example I wanted to talk about just for a second. To generate video, not to generate video, sorry, that's to absorb video. What we're doing in a machine learning context is to take hundreds or even thousands of GPUs and process the same data converge on some interesting piece of information. So we take a relatively small data set and we load it repeatedly, relatively small, meaning hundreds of gigabytes or in the low numbers of terabytes, and load that and process that in hundreds or thousands of GPUs in parallel, churn, compare results, repeat, churn, compare results, converge on an answer, then expunge, and then load again, and then load again, and load again. Thousands and thousands of those data sets. So every single workflow is different. Of course, the HPC workload that Gary and company have talked about, bursting sequentially into a bandwidth optimized medium, right? That's the classic HPC checkpoint model. Handling competing workloads that would otherwise thrashing spinning disk. Increasingly, we have customers who say, I've got thousands of scientists who just want to use this machine. They don't want to care about the I/O profile. You know, it's so complicated for us to just get jobs scheduled and figure out how to use the machine to 100%. If I also have to figure out what the storage infrastructure needs, it becomes too complex for us to manage. And solid state is really helping with that because it eliminates the seek profile requirement. Check the time here. Okay, cool. Then the many nodes of a single job in parallel example is where I have either a checkpoint restart or I have an I/O profile, in situ analytics, those kinds of things. Could be a file per process where I'm burping out a big checkpoint in many files. That can really introduce a metadata workload on the metadata subsystem because I'm trying to create and allocate space for a lot of data at once. But on the other hand, I could be allocating one monster file and then doing I/O into that file in an interspersed way. So I get lots of partial strike writes, like the DDO example. And so that stresses the I/O subsystem in a completely different way for an exactly identical workload depending on how the application is written. So understanding the details of the way the applications emit data and absorb data is critical. And also being able to articulate that in an RFP or in a workflows document is better. I mean, we can talk at the broad brush about how the data flows into the system and out of the system, but if we don't know those details, we may design an I/O subsystem that's inadequate for the job. So some implied requirements. I'll just read these to you. These are straight out of the document. Launch an application at full system scale in less than 30 seconds, describing factors such as executable size that could potentially affect the application launch time, describing the application's launch scales within the number of concurrent launch requests. And this is typical of an HPC application, right? So we want to basically load the same binary everywhere at once across 100,000 nodes or whatever that number is. So how do I interpret that request? And by the way, we solve this by a specialized storage infrastructure that lets us distribute these binaries and load it from multiple nodes at once, but that isn't a one-size-fits-all storage infrastructure. That's something that's specific to these kinds of use cases. So the answer, the translation is open a bazillion files at once, which is one requirement, and then also open and read a single file a bazillion times concurrently, which of course bottlenecks the system on that one single file if you don't distribute the workload. Right? So this is just something buried in a document. Oh, by the way, you need to do this. But it really has a significant impact on how you structure the storage system. So being very explicit about all the different ways that data is used, consumed, and emitted by the system is important. Another one, provide consistent run times, wall clock time, that don't vary more than 3% from run to run in dedicated mode and 5% in production mode. That's an easy thing to say. It's a really hard thing to achieve, right? And the DSSD guys have done probably the yeoman's job at achieving that. So we have to have what this means is the introduction of QoS controls both into the fabric and into the storage subsystem so that we can guarantee rate I/O. You know, as my new job starts and I allocate a bunch of storage, I need to make sure that storage is laid out in a way across the system that enables me to get the data in and get the data out consistently with the last time I ran this job. Right? And so that's no mean feat, because that means I have to keep track of how I did it last time so that I can do it similarly this time. Or I have to distribute the data so uniformly, regardless of when I'm running the job, time and time and time again, that it's guaranteed to be within a certain limit. Or I have to over-provision the system, which of course is expensive, and customers don't want to pay for that, pay the freight on that. So let me talk just for a minute about data work. This isn't, I didn't want to make a product pitch here. I'm going to talk about a data work use case in a second, so I need to give you some example for some information about it if you don't know how it works. So on the left, we have thousands of compute nodes on our Aries network. This is the green hexagon. I think they're hexagons, yeah. Hexagons up there. And then on the bottom right in the red here, we have data work nodes, which have a pair of NVMe half-life flash SSDs in them. And then they're directly on this specialized Aries network. Then we have these LNet router nodes, Lustre nodes that are carrying, there's, by the way, Lustre clients on the data work nodes too. And then the Lustre router nodes are carrying data through HCAs, just basically transmitting it. They're not catching any data, there's no storage in them. Through this IV fabric out to traditional Lustre OSTs on spin. Right? So that's really the topology of a data work configuration, of course at much, much larger scale. Doing terabytes per second kind of an I/O profile. So using this, I'll give you one Nastran example, one specific Nastran example. This is the only busy slide I've got. The rest is all big arm wavy, hand wavy kind of discussion. Maybe some of you have seen this before. To describe these charts, there are two charts, one above the other, and then on the left axis we have the position in the file that's being accessed. So at the bottom of the chart is the lowest offset, and at the top of the chart, each chart is the highest offset of the file. And so the red lines actually reflect where within the file the I/O is occurring. Right? And then the x-axis is all about the wall clock time that the job runs. So starting with the bottom picture, what we have is the write times in blue. So we write for a while, and then we begin to read. And we read from early offset of the file all the way out to some late offset of the file. And then we begin to read backward. So we start to read down through the offsets of the file. And what you see is this spike, and this is in the bottom graph. The spike comes halfway down, excuse me, and then the slope begins to fan out. And we repeat that process and repeat that process and repeat the process. The bottom chart is Lustre on spinning. So what's happening here is that the data is being read backwards, and as long as it's in the cache, access is fast. But when we exhaust the data that's in the cache, we have to go after the spinning devices. And spinning devices don't really read backward very well. And so we're inducing a lot of seek behavior. So what we get is these slope lines, slope line, slope line. And what that does is it protracts the duration that the job runs. Right. Now in the top example, because we don't have the seek latency issue on solid state, we put a data work infrastructure in here. And so this isn't just useful for checkpoint restart, it's useful for interesting kinds of I/O profiles that we see in jobs. So what we get is a very, very crisp zigzag line, because as we read backward through the file, even when we exhaust the cache, we can still continue to read with alacrity. And the job duration is dramatically reduced as a result of that. Right? And this is the kind of thing that we're seeing as a practical example, and there are many others of these that we're seeing as practical examples with implementation of a generalized flash optimized file system for HPC. So it isn't just about bursting out a burst bar. I'm just building the slide. Some frequently unanswered questions. I'll leave the discussion with two of these slides. Things that we don't hear from customers. they'll always tell us how many bytes they want. They'll always tell us how many files they've got. What they don't do is give us a profile, generally, of how many files of which size. Because it could be that there's a whole bunch of small ones and then a bump in the middle for a group of files that are mid-sized. Or maybe they are distributed evenly, so that there are a very small number of large files and smooth on back out. Not always the case, right? We don't get that profile information. What is the existing project? Is this new? Because if it's new, we have opportunities to influence the storage design. But if it's an existing product, we have a lot of baggage that's going to be carried forward. We have to handle the existing workload. We have to handle the existing workflow, which means we have to understand thoroughly how the system is currently implemented in order to increment that up. And the interfaces are going to be legacy that we need to adopt and handle, whereas if it's new application code, we can afford to perhaps force a certain block alignment that gives us better I/O profiles, or force a certain get-put style interface as opposed to a read-write interface. And so these are the kinds of questions that we like to ask. What is the current workflow? Do they really understand it? And how might we optimize or improve that over time? What are the drivers of change? They're buying the system for a reason. Is it just more of the same, like the other chart? Or is it some new thing that they're trying to accomplish? Because the I/O subsystem is an increasingly important part of a large computer subsystem. And we need to take an active role in making sure that the processing moves on unabated. What has to remain the same? What are the constraints on us that let us design, or that force us to design the I/O subsystem to meet certain requirements, prior requirements? Volume, veracity, variety, velocity. These are buzzwords in the industry today, but they're very, very useful in thinking about all the different factors that influence the storage subsystem design. What are the gazintas and the gazatas? These are my terms. I'm defining them here. Where does the data come into the system? Where does the data exit the system? And what does it look like? What interfaces are the applications expecting to see on the input? And what options do we have to change that? And likewise, where does the data come out of the system? And maybe for other people's use downstream that's outside control of the system. So what other systems does it have to interface with? Where does it originate? Internally, externally? That'll influence whether we have more requirements for downstream job flows. Frequency, format, data quantity, object quantity. I've covered some of those. This might be my last slide. And then what are the consumers? Like, who are the consumers? Who are the people consumers? Who are the application consumers of data? What is the concurrency of access? What are the granularity of access? Maybe these are 84-byte records that are accessed randomly. Maybe they're 840 megabyte chunks that are accessed randomly, right? We don't get this kind of requirement in a requirements document typically from a customer. We generally have to sit down across the table from them and whiteboard things together. So I really appreciate the detailed analysis that has gone into the Apex RFP and the Apex workflows document. One thing that our analysts who are actually doing computer models of the workflows are saying is that we'd like another couple of orders of magnitude of depth on each of the applications and how their I/O profiles operate over their lifespan, so that we can understand how they'll interact with each other when they're running on the system together, etc. So, and then of course, lastly, husbandry. How long does the data live? How does it get deleted, or is it to be kept forever? This forever storage concept is important, but in the intermediate stage, we have campaign and temporary storage. Who deletes that? Are we supposed to delete that or someone else? Right, and on those kinds of requirements can go. I could talk about an hour for each of these, but I won't. Hopefully this will give you some ideas and inspiration for how to think about specifying requirements for vendors such as ourselves, and I'm glad to talk with you about it afterward or read some of the documentation you produce and give you some feedback.
Great.